Let us understand a simple and effective approach for curve sketching of trigonometric function 2x minus tan x. I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll discuss curve sketching of a trigonometric function. It's a combination of linear and trigonometric function. F of x equals to 2x minus tan x, where x is between minus pi by 2 and plus pi by 2. We'll understand the function first, analyze the first derivative to find local extremas, maximum minimum values. Then we will analyze the second derivative to find the concavity and the point of inflection. Once we have all these critical points, we'll sketch the graph of this particular function. Let us first try to understand the function itself. So here, as you can see, we're talking about two different functions combined together. The function given to us is f of x equals to 2x minus tan x, correct? So 2x is a straight line which goes through the origin, which is going to be kind of like this, right? The interval is minus pi by 2 to plus pi by 2. And for tan x, we have the vertical asymptotes at pi by 2. So clearly, our domain is restricted to minus pi by 2 to plus pi by 2. And the boundary is defined by these vertical asymptotes. Minus of tan x. Well, generally, if you draw tan x, it will be kind of like this, right? Now, since we are given minus of tan x, it is going to be reflected on the x-axis and the graph is going to be kind of like this. So that is minus tan x for us. And the first one which we have drawn here is 2x for us. So now it is basically addition of these two. Perfect. Clearly, as you can see, when you add these two, there are points where if it is going to extreme value, the function will go to extreme value, correct? So those two extremes are kind of defined within this interval. We'll now figure out what happens in between with the help of first derivative, second derivative, their analysis. Perfect. So I hope you've got some concept about it. I'd like you to now pause the video, sketch the graph, and then look into my suggestions. Well, in case you want to learn from me directly, you can send an email on the address given. Most of my students are doing extremely well. They're right there on the top of the class getting awards and scholarships like Akshay.
After attending university. The winner of this year's Certificate of Achievement Schulich Leader Award is Akshi Kandivani.
Great. Our student Akshat gets highest marks and the most prestigious Schulich Leader Award. You can be there. Join our classes and excel. Now, let's move forward with this particular function. Now, some of you might have observed something very typical about this equation, which is f of x equals to 2x minus tan x. Well, what can you say about the symmetry of this? 2x is an odd term. Tan x is also an odd term, though we expect odd symmetry. Let's prove it. So if I try to find what is f of minus x, I get 2 times minus x minus tan of minus x, correct? So that gives me minus 2x, and this is now becoming plus tan x, right? Minus of minus, and we can take minus outside, factor it out. So we get 2x minus tan x in the bracket. Perfect. Now, which is equal to what? That is minus of f of x. Perfect. Since I've shown that f of minus x is equal to minus of f of x, what kind of symmetry is there? There is odd symmetry. So that helps. Odd symmetry means it is symmetric about origin. Perfect. So we have discovered one more thing about it. Now let us continue with the derivative part and its analysis. Function f of x is 2x minus tan x, and the first derivative of this function is what? Well, derivative of 2x is just 2 and tan x is secant square x. To find the critical numbers, we are going to equate this to 0, right? So that is to find the critical numbers. Now, secant square x is equal to 2. That means secant x is square root 2. So clearly you know what the angle could be, right? Pi by 4, right? So let me just sketch here the triangle of our interest. And as you know, the sides are 1, 1, square root 2 for the angle x, right? So we know secant x of square root 2 means x is equal to pi by 4, right? So that happens when we have this angle as pi by 4, right? Isosceles right triangle. So pi by 2 is a critical number. Now you should remember one thing, and that is we are talking about a domain which is from minus pi by 2 to plus pi by 2. What does that mean? Let's try to look into this. So minus pi by 2 means you're going in this direction, right? So that is minus pi by 2, correct? And this is plus pi by 2. Correct? So you're looking into this particular domain, and in this domain, you know the cast rule. So in this particular domain, as you can see, we have two values of x. One is pi by 4, the other one will be minus pi by 4. You get the idea? So we have two different values, one in quadrant 1, the other one in quadrant 4. Now this is for both positive values. In fact, this will be positive and negative, but given in the condition, which is between minus pi by 2 to pi by 2, we only have secant x equals to positive value of square root 2, correct? Not the negative one. And therefore, for this particular positive value, we have our critical number, right? And that gives you two values of x. One is x equals to pi by 4, and the other one is minus pi by 4. Absolutely clear, right? I'm repeating it purposely, since we have to restrict ourselves to the given domain, right? Now what you need to do is you need to analyze this to find whether we have a maximum or a minimum, local maximum minimum at this critical point, right? So our derivative is 2 minus secant square x. Let's analyze it. So we found that the derivative for the function, which is given to us as 2 minus secant square x, we found that the critical numbers are at plus and minus pi by 4. So we will analyze. So let me just sketch interval table for you, right? And let's take some values. At pi by 4, negative, right? And positive pi by 4. So within that, let's take some test points. So a good test point on the left side of pi by 4 will be what? Well, in between, no problem, 0, right? On the right hand side of this, more than pi by 4 will be pi by 3, right? And less will be minus pi by 3. As soon as I write pi by 3, it's a good idea to look into your pi by 3 triangle, correct? Which is 1, 2, square root 3. Right. Now we are looking into 2x, and the other factor is minus secant square x. Correct. So as far as 2x is concerned, if I give a negative value, it is going to be negative, right? And if I give a positive value, it is going to be positive. Sorry, the factor is not 2x but 2, right? Okay. Right. So now, let us analyze the first derivative, which is 2 minus secant square x. So if I write 2 minus secant square x for minus pi by 3, then what do I get? Let's figure this out. 2 minus secant square x. Well, remember one thing, that for pi by 3, whether it is positive pi by 3 or negative pi by 3, the value of secant x is going to be positive, right? Because you are in these quadrants. And we know that secant pi by 3 is going to be hypotenuse over adjacent side, which is 2, right? So square will be 2 square 4, right? And therefore, secant square pi by 3 will be equal to positive 4. So when I substitute minus pi by 3, I get 2 square, which is 4, and therefore I get a negative value here, right? And for 0, we know it is 1. For 0, secant 0 is equal to 1, correct? So 2 minus 1 will give us a positive value. And when I put pi by 3, then I get again a negative value, since it is 2 minus 2 square, which is 4. So what we figure out here is that our function is negative before minus pi by 4, right? Then positive. So as far as function is concerned, it is going to go a downward trend and then up and then down. So clearly what we have here is at minus pi by 4, we have local minimum. And at plus pi by 4, we have local maximum. So let me write maximum and minimum in the bottom. It'll be easier, right? So we get our maximum and minimum points, right? So we have their values. Let's put these values in the function itself to find the maximum value, right? So what is f of minus pi by 4? So f of minus pi by 4 is the minimum value, which is 2 times minus pi by 4 and tan x. Tan x is negative here, right? 1, negative 1, right? So it is minus of tan of minus pi by 4 is negative 1, so it makes it positive. So we have a value which is negative pi by 2 plus 1. 1 minus pi by 2, right? Now pi by 2 is greater than, so this is a negative value, right? Now let's look into plus pi by 4. So we get 2 times plus pi by 4, and this becomes positive, right? So positive and minus of tan x will give me negative 1. So we get here pi by 2 minus 1 as the maximum value, right? So what are we doing? We are evaluating the function f of x, which is equal to 2x minus tan x at minus pi by 4 and plus pi by 4. Correct? You can always use calculator to find these values. I'll leave them as such, okay? See, pi is 3.14. So dividing by 2 gives you more than 1, right? So this value, you can see, is greater than 0, and this value is less than 0. Is it okay? Perfect. And they are symmetric. Now, let us analyze the second derivative. So we just found that the first derivative for this function is 2 minus secant square x. So what is the second derivative? Well, the second derivative will be derivative of 2 is constant. We have minus 2 times secant x times derivative of secant x. So we get here minus 2 secant x times secant x tan x. Correct? And that gives us minus 2 times secant square x times tan x. So that becomes the second derivative. Now from this second derivative, can you find the critical numbers? We're looking into the interval minus pi by 2 to plus pi by 2. So in this interval, tan x is 0. For x equals to 0, right? So if I substitute 0 for tan x, that really implies that tan x can be 0, right? And that happens for x equals to 0. So we have one critical number here. So our critical number is at x equals to 0, correct? So there could be a point of inflection at this point where the second derivative is 0, correct? So second derivative is 0 for tan x, right? And we are talking about this interval. Remember that. So let's try to analyze this. So we'll analyze on either side of 0. So we can go to the right. Let's say test point be pi by 4 and minus pi by 4. Right? Good points to take. And our second derivative is what? Well, the second derivative is equal to minus 2 secant square x tan x, correct? Now secant square x will be positive. We have minus here and tan x. So if I substitute a value which is minus pi by 4 here, then what happens? In that case, tan x will be negative, and this negative will make it positive, right? So in this portion, let's rewrite these terms like this, right? So we have three factors, right? Minus 2 is 1. Let me rewrite each. Minus 2 will remain negative. Then we have secant square x, which will become positive, right? Because it's a square term. And then we have tan x. So these are the three things we are looking into. Tan x will be negative because this is in quadrant 4 and positive in quadrant 1. And when you multiply all of them, what do you get? Easy, right, to understand? So two negatives makes it positive and one negative is negative. So clearly we have change in concavity. So what we notice here is on the left side of 0, we have concave up, and on the right side, we have concave down. Do you see that? And we have a point of inflection at x equals to 0. Make sense? So at x equals to 0, we have a point of inflection, correct? On the left side, it is concave up, and on the right side, it is concave down, right? So now let's figure out all these points, right? So what we found here is that broadly speaking, we found that the concavity, so it is from minus pi by 2 to 0. Within this interval, the graph is actually concave up, right? And from 0 to pi by 2, it is down. And therefore, in between here, we have a point of inflection. At x equals to 0, correct? So the basic graph is going to be like what? So on this side, it is going to be kind of like this and then like this. Do you see that? Perfect. So that is how the graph is going to be, right? So now you have all this information. Let us summarize this information once and then sketch the graph. So what we have here is, so we have all this information. We know where the concavity changes, and this point of inflection happens to be at 0. Now, let us actually sketch the graph. So let me again draw the axis, x-axis and the y-axis. We're looking into the interval from minus pi by 2 to plus pi by 2. Tan x, we know, has got vertical asymptotes at minus pi by 2 and plus pi by 2. So whether you add or subtract anything, it is going to remain same, right? Infinitely large. So those are at minus pi by 2 and plus pi by 2. Let's say equals to x or x equals to this, right? So these are the vertical asymptotes. We have a 0 at 0, then you plug in 0, right? So critical point f0 is 0. And we figure out that at pi by 4, we have maximum, right? So f of minus pi by 4 and plus pi by 4, let me write down. And f of plus pi by 4, we have local and maximum minimum values, which we found as at minus, we have a minimum value of 1 minus pi by 2. We can write minus pi by 2 plus 1. Okay. And this value is pi by 2 minus 1, right? We also found that this is symmetric, odd symmetry. So it's good to summarize, right? So that is one piece of information. Then from the second derivative, we found concavity, right? From minus pi by 2 to 0, right? And down from 0 to pi by 2, correct? And point of inflection right there. So looking into this, we can actually sketch the graph. As, let me just sketch it better, right? There is a vertical, kind of like this, right? So now we know that the maximum minimum points are at this point, which is at pi by 4 positive and negative, correct? And the value is minus pi by 2 plus 1 and plus pi by 2 minus 1, correct? So that becomes the graph of our function f of x from the details. Now it is very difficult to find the x-intercepts. We clearly know that the graph behaves like this from concavity. We don't know exactly where it crosses. For finding these points, you need a graphing calculator, okay? So for simple calculations, it's difficult to figure this out. So I hope with this you understand the complete concept of how do we sketch the graph for a trigonometric function when it is combined with a linear function. So I like you to see the basic which we looked into, right? Do you see that? So here if you analyze now, the tan function dominates in this portion, right? Going to infinitely large values. Is that clear to you? 0, of course, will be 0. And in between, the portion where it is less than 1, in this particular portion, the line dominates. You get the idea? 2x dominates. And therefore, what we get is the graph, which is kind of like this. You see that, correct? So I hope with this you understand how do we go about in curve sketching, especially when trigonometric functions are involved. Feel free to write your comments and share your views. In case you like and subscribe to my videos, that'd be great. In case you want to learn from me, you can directly send an email on this address or check our website for latest updates. Thanks for your time and all the best.